Hey guys, so this is chapter 11.2, areas of circles and sectors and area of sectors. So, recall from the last section we dealt with uh, arc length in degrees and arc length in units. We're now dealing with the area. So, if you recall, the area of a circle is pi r squared, where r is your radius. Remember that radius is half of the distance from the center of the circle out to the end of the circle, and it is half the length of the diameter. So I'm pretty sure you guys can easily find the radius. First theorem of this section. Then they talk about something called the sector, and the sector, as the book calls it, is the region bounded by two radii of the circle and the intercepted arc. Meaning, here's our circle over here, uh, circle P. Uh, this is our inbounded radii, meaning more than one, in this case two. So from P to A is a radius, from P to B is the radius, and this particular sector, everything in yellow, is the sector. It's just a part of the circle being cut out between two radii and the intercepted arc. So this is the intercepted arc of these two radii, and we call that the sector. And the next theorem deals with finding the area of the sector, which is very similar to the proportion that we did in the last section. And it says that the area of the sector divided by the area of the circle is equal to the arc length in degrees divided by 360. So the area of the circle, actually that's wrong, the area of the sector of the circle over the area of the circle is equal to the arc length in degrees. I'll just put the arc over 360 degrees, which is the degrees of a whole circle. So that is our uh, proportion when we're trying to solve for finding the area of the circle or for the area of the sector. Uh, they rename it by saying that the area of the sector is equal to the measure of the arc length over 360 times the area of the circle. But it's just renaming the same exact proportion. So with that information in mind, we can find some things. So down here, they give us a circle, D. They want us to find the area of the circle and the area of the red sector and then the area of the blue sector. So in order to find the area of the circle, all you need to do is find a radius. In this case, the radius is 14. Note that our area of the circle is pi r squared. So in this case, it's going to be pi 14 squared. And 14 squared is 196. So you can say it's 196 pi if you want to do it in pi form, or you can multiply that out and say that it is 615.75. 615.75 feet squared. Either way works. Okay. Once you do that, if you want to find the area of the red sector, notice that the red sector is 121 degrees. That's our arc length in degrees. So if we use our equation and say that area of the sector over the area of the circle, which we have as 615 over 0.75, is equal to 120 over 360. So then we can get area of the sector is equal to 120 or 12 over 36, cross off my zeros, times 615.75. So that will give me approximately 205.25 feet squared. So that's how you get the area of the red sector. To get the area of the blue sector, first thing I do is got to get the arc length in degrees. So I'll do 360 minus 120, and that's going to get me 240. So the area of the blue is 240 degrees. So I'm going to use that same equation. Area of the sector is equal to 240 over 360 times 615.75. That's going to give me approximately 410.5 feet squared. Or once you have gotten the first one, the first area sector, you could have subtracted the 615.75 minus that. That would have given you the same answer. Okay, so that's the first part. If you want to find the area of the circle, you can use the same exact proportion based off the information they give you, and you can find the area of the particular circle. Since we have the sector area equation proportion, we can actually use it to find shaded regions of complex shapes. So in the case of this, we have a rectangle that's 26 by 36. We have a semicircle, and we have a square. So they want to know the area of the shaded region. So the book says that we're going to subtract the area of the entire rectangle minus the semicircle plus the square. Notice that the side of the semicircle is the same, or the diameter of the semicircle is the same as the side of the square. So if it's 16, then the radius is 8. And since it's a semicircle, something that the book does that I don't agree with is it does the proportion and it says 180 over 360. Since we know it's a semicircle, we could just say that that's 1/2. So instead of saying 180 over 360, we'll say 1/2. So what they do is they get the area of the rectangle, And the area of the rectangle is 26 times 36. And that's going to give me 936. You're going to subtract the semicircle and the area of the square. The area of the semicircle is 1/2 pi 8 squared, and the area of the square is 16 times 16, or 16 square. And the book says that that is 32 pi plus 256. 32 pi is 100.5.53 plus 256. And the book says that it's about 579.47 feet squared. So you guys are going to be doing a lot of complex shapes and subtracting out from circles and other shapes as well. Should be good times for you guys. So down here at the bottom, they give us a couple problems. They want us to find the area of circle H. They give us the area of the sector. They give us the arc length in degrees. So we have enough information. So area of the sector over area of the circle is equal to the measurement of the arc length of, in this case, FG over 360 degrees. So that's going to give me 214.37 over the area of the circle is equal to 85 over 360. Okay, so since the area of the circle is here in the denominator, I would probably want to flip these and do the inverses. So area of the circle over 214.37 is equal to 360 over 85. Then multiply both sides by 214.37. These guys will cancel. And then I have the area of the circle will be equal to 360 divided by 85. Times 214.37. And I get that the area of the circle is approximately 907.92 centimeters squared. Here we have, for number 5, area of a complex shape. We have a right triangle and we have a semicircle. So in order to add that up, we're just adding the area of a semi plus the area of a right triangle. So we have a diameter of 7, which is also one of the sides. This looks like it's an isosceles triangle. So we know that the radius is going to be half of that, which is 3.5. So 1/2 pi 3.5 squared plus, for area of a triangle, we know area of a triangle is 1/2 base times height. So it's 1/2. In this case, the base and the height are the same. number. They're both 7. So 1/2 7 times 7, or 7 squared. So 3.5 squared times pi divided by 2. I get about 19.242. So 49 divided by 2. 24.5. And I get about 43.74. And this is going to be units when you solve these. Your units are always going to be squared when you do area. Alright, so this last question is a word problem. They say if you know the area and the radius of the sector, can you find the measure of the intersected arc? So they're asking if you can find the arc length, and the answer is yes. So if we look at our equation, area of the sector over area of the circle, that's equal to the measurement of the intersected arc. That's what they want you to find, over 360 degrees. So all you have to do is multiply 360 on both sides, and that should give you what you want. So then your final equation is going to be 360 times the area of the sector over the area of the circle, and that's going to give you your measurement of the intersected arc, or your arc length. So if they do give you the sector, and if they do give you the area of the circle, and they said if you know the radius, yes, then you do have enough information to find your arc length. Okay, so those are the questions and examples involved with this section. Uh, this section will make you think a little bit in terms of finding uh, the area of the shaded region, but not anything that you guys can't handle. So that is 11.2. Have a great rest of your day, guys. Take care.